If you've seen any of my previous videos on audio processing, you'll have noticed that I've been using the Digilent pMod I2S2 board as codec. And here's a, let me just zoom into that here. You can see the board has line in and line out. And then on the right-hand side of the board are all the I2S inputs, which I've described earlier, and I'll provide a link to those videos down below. Now, I'm a big fan of the pMod board, but I've been looking for a while for a board that exposes the audio in and out as pins rather than as 3.5mm jack. And I recently came across this board that you can see over to the right-hand side there. Let me just pan in on that so you can get a close-up view of that board. So this board here is the PCB Artists ES8388 board, and I thought I'd buy a couple, give it a go, and share the results. Now I purchased these boards myself, and I'll provide a link below if you're interested in getting a hold of some yourself. So not only does this board expose all the signals, line in, line out, so all the digital signals are on the left-hand side here, and we'll go through a pinout in a little bit, but not only does it expose all those signals as pins through a pin header, but the ES8388 is the codecs that's used by Espressif's LyraT audio dev kit, and so there is full support with a few bugs that I'll go through below in the ESP-ADF, the audio development framework for it. I'll include a link to the ES8388 datasheet below, but another key difference to the pMod is there's an I2C interface that allows control of the internal ADCs, the DACs, etc. In fact, pretty much everything you can see on the block diagram can be programmatically controlled. So let's have a quick look at the block diagram, and then we'll move on to the pinout. Here's the block diagram for the board here. It's all kind of conceptual, but you've got line in, line two, both left and right channel. You've got down the bottom here, you've got the serial audio data interfaces. So this is the LR clock that we've covered before. You've got I2S data out, I2S data in. Here's the bit clock or S clock. And then finally over the left-hand side here, we've got the master clock. Now, I'm operating this in slave mode, so all these signals come from the ESP32. But you can see internally, you have all these sub-modules, and you can control pretty much any of these sub-modules through the I2C interface. So for example, there is a part of the I2C interface that allows you to control the gain of this amplifier component right here. So signal comes in here, you can programmatically control the gain right here before it passes on to other parts of the ES8388. Okay, so here's the pinout diagram of the board together with the default GPIOs. And this comes from a link which I'll share on the PCB Artists website. Now, if you hook up your ESP32 to these default pins, you can pretty much use the LyraT 4.3 board out of the ESP-ADF, and I'll kind of show you how you select the board a little later on. And then you're good to go from there. Note on the board here also, there's multiple grounds here. So we've got a ground here, a couple of grounds here. Now these are all tied together, so you just need to ground one of them. And then, you don't need to sort of have a ground line on each one of these grounds here. Just so I've chosen this one to ground. Now, there are two different voltage supplies, though. So we've got a digital voltage supply over here and an analog voltage supply over here, and they are not connected together. So I think the idea is that you connect your two supplies separately, and then you don't have sort of high frequency noise leaking into the audio circuitry. But I've got them simply hooked up together, and that might explain some of the high frequency noise I'm actually getting in the output here. But the board does give you the option of hooking them up separately. Just a quick note, there are actually three, on the ES8388, there are actually three VDDs. There's a VDD DVDD, and there's also an HP VDD, which is the headphone VDD, and they're actually just connected together on the board here. The final note here is these two pins here are for a microphone, a separately supplied microphone bias, if you wish to do that. I'm actually not using the microphone here. I'm using RIN2, LIN2, and R-out and L-out, but more to come on that later on. So I chose to, however, not use the default ESP32 pins, and I've gone with this diagram right here. Now, the main reason for that is the board that I'm using does not have GPIO 0, which is used for the master clock exposed. So I'm using GPIO 3 for that. Master clock is one of the exceptional interfaces in that you can't map master clock to, unlike the other GPIOs, you can't map master clock to whatever pin you want to. You've basically got a selection of GPIO 0, 1, or 3, and that's it. And you do have to do some magic code, which I will walk through later on. So you can see the pinouts right here that I've got set up here. So D out to GPIO 19, LR clock to GPIO 18, data in, which is data out from the ESP32 is 21. Bit clocks on GPIO 5. Now this is the master clock here, and it's on my board. It's called RX0, but it actually maps to GPIO 3. And then I've got SCL and SDA for the I2C interface there on pins 23 and 22 respectively. On the input and output side, so here's the audio signal coming in, and I've got that coming into RIN2 and LIN2 on the board. As I mentioned, I've got my AVDD here just connected to 3.3 volts, and that's the same 3.3 volt source. And then on the output side, basically I've got it going through this simple low-pass filter here that consists of a 220 ohm resistor and a 0.1 microfarad capacitor before it actually goes out, and I've got it going to my oscilloscope. So here's the actual board I've got set up here. Here's all those digital lines, the data in, data out, LR clock, master clock, and so on and so forth, going over to the right-hand side of the PCB Artists board. And then here's the input lines coming in here to RIN2 and LIN2. And then here's that simple low-pass filter here. There's that 0.1 microfarad cap, and there's a 220 ohm resistor before it goes out. And then this is audio out. So audio in down the bottom, audio out at the top. Okay, so let's start with a simple example here. And I'm not in the first example I'm going to show you, and I'll walk through the code. I'm not using the ESP-ADF. I'm just kind of programming the ES8388 I2C interface manually using a copy of the code from the ESP-ADF. But what I'm basically doing here is I'm just generating a tone and varying the amplitude. So you can see on the oscilloscope there that amplitude is waxing and waning, and let's just hear that. So you can hear that. Let me just change the frequency so I can kind of prove that I'm not faking it here. So let's go up to, let's say, 1000 hertz. Now, one of the things I've noticed is as you're programming it, you get a lot of noise on the output there. So there's 1000 hertz tone, amplitude varying as before. Okay, so let's just quickly walk through some of the code here. So as I mentioned, this piece of code isn't using the ESP-ADF. I'll provide a link below to the GitHub repo for this. So what I've basically done is take the ES8388 code out of the ESP-ADF and just basically copy it into this file. So pretty straightforward stuff. Let me just walk you through some of the highlights. This code we've seen before. This is just the ESP32 I2C setup, which you need for the codec. Just moving down to the initialization. So this is all through the I2C interface, and it's basically powering up the chip, powering up the DAC and the ADC, setting some volume, just some setup code there. Just moving quickly on, this configures the I2S interface on the codec. So this is different to the I2S interface on the ESP32. And there's two sections here. The first is the format, and that's just simply, really you've got a choice between I2S or a standard PCM. So this just sets I2S. And then the second portion sets the sample bits length. Now, the sample bits length, we've covered that before in I2S. I'm using 16-bit samples here. But the interesting thing is you have to set that both on the codec as well as in the I2S, which we'll see below. Okay, so just moving down to the ES8388 initialization code, and as I mentioned, this is all over I2C. So you can see here, I pulled this initialization code directly from the ESP-ADF. This would be tough to derive myself, but basically involves powering up the chip, setting the the I2S mode. In this case, this is in slave mode, and what that means is the LR clock, bit clock, and master clock come from outside the codec. It powers up the ADCs and the DACs. Moving on down, next section of interest is configuring the I2S on the codec, and that's different to I2S elsewhere. And what it basically does here is it sets the format. And the format can be one of I2S, I think there's a left justified, right justified mode, and a DSP PCM mode. And then moving down a bit further, we have the sample bits length here. And as I mentioned, the sample bits length, you have to set it on the codec, and you have to set it separately in I2S, and they have to match. So you can see here I'm setting this through the I2C interface, and as we go down a little bit further, you can see I'm also setting that sample bits in the I2S configuration. So just moving back up, after you've finished initialization, you then run this start function here, and that actually fires up the chip and starts processing inbound, outbound audio and I2S signals. Just one quick note, this is the magic code that I alluded to above to set the master clock pin on the ESP32. As I mentioned, you can't use any pin for master clock, and in fact on the ESP32 you are limited to GPIO num 0, 1, and the final one is GPIO pin 3, which I'm actually using. And this magic piece of code I actually got out of the ESP-ADF. I probably would not have been able to work this out myself. So moving down a bit further, we have the actual ESP I2S configuration here. I'm in master mode. I'm only transmitting data to the codec. This is the sample rate, and the sample rate I'm using here is 44.1 kilohertz. Now, you don't have to actually tell the codec what your sample rate is, only the bits per sample, which is here. So this bits per sample here has to match the bits per sample that you set above when you are configuring the codec. Just moving on down, here's the set of pins that I'll be using for the bit clock, word select, or the left LR clock, data in, data out. And they can be pretty much any pins on the ESP32. You're not fixed to a specific set. You then install the driver. You tell it what pins that you're going to use from this struct here. You invoke the master clock GPIO select, which we went through above, and then finally call set clock. And what set clock does is, for a given sample rate, so that's 44.1 kilohertz, a given bits per sample, 16 bits in this case, and then this number is how many channels, so we've got left and right channel. And then once you've got all the I2S set up and the codec set up, it's a simple matter of this I2S write function basically takes what is ever in the TX buff, and in this case it just happens to be that simple sine wave, and it sends that out through the I2S. And really, once you get to this point, interacting with I2S couldn't be simpler. There's no worrying about interrupts or DMA buffers. That's all handled under the covers. Of course, you can do all that yourself. This is all part of the ESP-ADF, so you know, you can interact directly with the I2S registers yourself if you so desire. Okay, so finally let's do something a little more interesting with the I2S. And here I've demonstrated this software in an earlier video, but this is using the ESP-ADF together with the DSP library to do phase shifting. So I've done this in quite a few videos before, and I'll include a link to a few of the other videos that has more details on this. But what you're basically seeing here is I'm injecting a 700 Hertz signal in phase to here, and it's being ingested into the PCB Artists board here. It's then being sent over I2S to the ESP32 right here, and we're doing phase, basically there's a finite impulse response filter that's running in here that does phase shifting. Then it sends it back out to the board. So the result of which is basically the left channel's getting shifted back 45 degrees, the right channel's being shifted forward 45 degrees, and the result being you've got those two audio signals now 90 degrees out of phase. So I've done this before just to confirm that. I'll turn XY on. You can see there's the perfect circle, as you would expect, for two signals at 90 degrees out of phase with one another. And so what I'll do now is I'll just move on to a quick walkthrough. I won't go into the details of the finite impulse response code. Like I said, I'll give a link to that. This is the same code that I was running using the pMod board, so it's good to see it all working together. But let me quickly walk through the changes that I had to do to get this working with the ES8388 board. Okay, so let's just go through some of the changes that I made to the code, and starting with the ES8388. So this is the main driver file for the ES8388 codec, and I noticed a couple of things, you know, at least they weren't working for me. So the first one's this line here. This was originally 0xBB. And this is the mic channel, sort of the input gain on the line in, and I found BB to be too high. In fact, the 0xBB wasn't even in the documentation, so I turned that down a little bit. The other change that I made is this function here, set voice volume. What I noticed is that these two both set the volume to 0. So this is setting the output volume of the DACs, and this is route 2 and lout 2, or lout 2 and route 2, I'm not sure. But these were both set to 0, so you would get nothing out of rout or lout 2 if, you know, in the original code. Okay, so then moving on, back in a previous video I show how to add your own custom boards. So basically you create this board directory, and it defines the pins and some startup code for whatever board you want to add to ESP-ADF. So I added this PCB Artist _ES8388 board, and in that board there's a couple of files here, a couple of important ones. Board pins config contains the GPIOs for the I2C as well as the I2S, and it also contains that bit of magic code that I showed you before, where this one happens to hard code the master clock to pin 3. I took a copy of this from the LyraT 4.3, so this is pretty much a bare bones version of that. The LyraT has a whole pile of additional features that the PCB Artist board just doesn't have. It's just the codec. So that's the changes there. And once you add that PCB Artist directory, you can then see that will appear now in sdkconfig as a board option. So if we have a look in Audio HAL here, so you can see that's defaulting to the LyraT. Now I can change that to, there you go, there's the PCB Artists board there. So so there you go, there you have it. That is the that's all I plan to do in this video. Hope you enjoyed this video. I guess the upshot is the PCB Artists board worked for me. It was relatively straightforward to set up, and consider it if you're in the market for a codec. That's all for now.